Swayam Prabha, free DTH channel for education.
Hello everyone, welcome back to the online video lectures of the medical imaging course. In this video lecture, we'll discuss about sampling in the spatial domain. To simplify things, let's start with 1D sampling and then we will move on to 2D sampling. Okay, let me move on to the notebook mode now. We are going to start with 1D sampling case. We'll call, for example, the 1D spatial domain function as f of x, and let the CTFT of it be capital F of k subscript x. This is your x. You are plotting your f of x here, which is a continuous function. Now what you would like to do is to retain its values only at regular intervals. Assume that you want to retain its values at a regular interval of x naught. So that would be x naught. Okay, at 2x naught you want to have its value, and 3x naught, and so on you would like to do. So how can you do that? One way that you could think of is multiplying it with an impulse train. For simplicity, I'll draw it just on the positive side, but the other you could extend if you want. So you have, if you multiply it with an impulse train which has a periodicity of x naught, then you would of course retain its values only at that particular points. So you want to have here impulses, this distance being equal to here also x naught, and after that the values are repeating at integer multiples of x naught. So let's call this function by name s of x. Okay, so this is what you are going to do, and as a result of multiplying f of x with s of x, you are getting a new function. Let's call it as f subscript s of x. So what would be that function now? So originally this has, let's say, f of x envelope is like this. Now you are retaining its values at integer multiples of x naught. So you have this function value at 3x naught, let's say, right, and this is 4x naught, and so on. This is your x. Let's call this function as fs of x. Right, now let's make some more assumptions here. Assume that the function I have is a band limited signal, and then I'm computing the continuous time Fourier transform of it. That would be, let's say, of this shape. This is your kx value. For the sake of simplicity, you consider the magnitude to be 1. Of course you could consider anything there, and here let's call this as xl here, the maximum value. Also assume that this is symmetric. This is capital F of kx, right? Now let us come to this impulse train and let's see how it would look like. For that, let's first write the expression for s of x also for the sake of completeness. So s of x is equal to, you have impulses from minus infinity to plus infinity. Delta of, you have it in the x-axis, and at all integer multiples of x naught you have it, right? Now what would be the Fourier transform of it? So capital S of kx, what would be that value? So this you have worked it out in your examples. This will have a multiplication of 1 by x naught, and your n varies from minus infinity to plus infinity. You have impulse in the kx space. Now if they are spaced at a distance of x naught, here they would be spaced at a distance of 1 by x naught. So you have kx minus n by x naught. This is your the Fourier transform of the impulse train spaced at a distance of x naught. So let's plot the same thing here. The CTFT of it would be, although it's from minus infinity to plus infinity, for the time being I'm just plotting it from 0 to infinity. So the earlier magnitudes are getting multiplied by 1 by x naught here, and there is a periodic impulse train again here, the distance being equal to 1 by x naught. Say for example this is 2 by x naught, 3 by x naught, and so on. This is your kx axis, and this is your capital S of kx. Now what we would like to further figure out is what would be the CTFT of this sampled version of f of x. To do that, what we would do is, let's write the expression first for the resulting function. Let us call that new function as fs of x, sampled version of x. This is obtained by multiplying your original f of x with impulse train s of x. So the impulse train, this s of x, right? Now you would like to look at in the Fourier domain, fs of kx would be now equivalent to multiplication in the spatial domain would be equal to convolution there. So f of k subscript x convolved with capital S of kx, is it not? Now that I could write it as f of kx convolved with summation of n varying from minus infinity to plus infinity, delta of kx minus n by x naught. Okay, and of course there is a multiplication factor here, which let me write it here. Notice that this f of kx convolution summation I could bring it out, and convolution I could take it inside, and then there is a shifting property here. Convolving a function with a delayed impulse will eventually delay the original signal by the same value. So use that property there, which would give me now both interchange of summation and convolution. This I could take inside, and then convolution with a delayed impulse would eventually delay my signal by the same value. This would be the expression for the Fourier transform of fs of x. Very important expression. So what is now happening? Once you are multiplying it with impulse train in the spatial domain, in the frequency domain you are going to keep multiple copies of it, and they are spaced at a distance of 1 by x naught, and of course there is a multiplication factor overall by 1 by x naught. So let's try to draw the same here. This is your kx. the first anyway n equal to 0. For example, you have a copy. We assumed that this has value from plus xl to minus xl here. Earlier we assumed magnitude is 1. Now that's getting multiplied by 1 by x naught, right? This is 0. And then next copy, for instance, is placed at when n equal to 1 at 1 by x naught. So here when you have 1 by x naught, one copy is placed. Similarly 2 by x naught, another copy is placed, and so on and so forth. And in similar lines on the negative axis as well, where this is, let's say, minus 1 by x naught, minus 2 by x naught, and so on. And this is your fs of k ex, correct? Now you already know sampling theorem, so I'm not going to go through it in a very detailed manner, but I would right away go to when can we recover f of x from fs of kx. That's the question here. So of course, when there is no overlap between these repeatedly placed copies, by using a low pass filter and just extracting one copy here, okay, and this low pass filter having a magnitude of x naught would eventually give you f of kx. So that means you are keeping copy at 1 by x naught. Within that, here this length is xl. Similarly, magnitude of this length is also xl. So 1 by x naught should be at least equal to or greater than 2 times of xl. So this is your Nyquist rate. As long as this is possible, you could recover your f of x even from the frequency spectrum of a signal obtained by multiplying the original signal with an impulse train. Otherwise, aliasing effect is there. Okay. Now let's go to 2D sampling case now with this background. Instead of f of x, now we move to f of x comma y. The CTFT of it, let's call it as f of kx comma ky. So here also you have a function in 2 dimensions now that you would be multiplying. Now you want to take samples of it both in the x and y direction. I want to take samples of it of f of xy in both x and y directions. Say in x direction I want to take samples with a spacing of, let's say, x naught, 2x naught, and so on, right? And in y, let's say I want to take samples with a spacing of y naught, 2y naught, of course here minus y naught, minus 2y naught, and so on. So how should be by impulse function now? This has to be, so this is x naught for all, but this is how I could say at all the grid points, right, which are spaced at a distance of x naught along the x-axis and y naught along the y-axis. So at all those points I'd like to take samples of my original signal. So then how does the impulse train function would look like then? So you have here an impulse along x. For example, these are the cases where your y equal to 0. You have all these points here, impulse functions here. Similarly, let's say for y equal to y naught also, you are going to do a similar stuff here. So you have an impulse train here at all these points, and of course for 2 y naught, and then vary all values of x naught, right? And of course you have to do a similar stuff for negative values of x and y. X anyway we are already doing there. For negative values of y as well, we have to take these samples. So this should look something like this. So what you have here, is a bed of nails, right? So let's write the impulse function for this. How does it look like? Delta of x comma y is equal to, now let me write m for variation along the x-axis, minus infinity to plus infinity, n varying from minus infinity to plus infinity, delta of x minus it all multiples of x naught, so I'll write m x naught, and similarly y at all integer multiples of y naught, so I'll write it as n y naught, right? So then assume that I'd like to take the Fourier transform. I'm now going to construct a new function f of s of x comma y, which is obtained by multiplying the original function f of x comma y. Let me not write it as delta of xy because that's a single delta, it's an impulse train sampling used for sampling, so I need that as s of xy. So this is equal to s of xy. Similar to what we did earlier, here also in the Fourier spectrum, this would be equal to fs of kx comma ky would be equal to capital F of kx comma ky. Multiplication in the spatial domain is equivalent to convolution in the frequency domain, capital S of kx comma ky. So you need Fourier transform of this 2D impulse train, right? What would be that? S of kx comma ky will be equivalent to, well, since you have spacing at x naught y naught similar to our 1D function, the magnitude gets multiplied by 1 by x naught into 1 by y naught. Then you have summation remains, impulse train would still give you an impulse train. So I am writing m varying from minus infinity to plus infinity, n varying from minus infinity to plus infinity. Now your parameter here is kx now in the frequency domain. If they are spaced at a distance of x naught in the time domain, it would be 1 by x naught in the frequency domain. Similarly, if it is y naught in the spatial domain, this would be equal to 1 by y naught in the frequency domain. So that's your impulse train's equivalent Fourier transform here. So this is your CTFT of it here, right? Now what about fs of xy? You convolve the Fourier transform of f of xy, right, with this. So then again I'm right away writing this, since we have already done it here for the 1D case here, right? So the multiplication factor here would be, of course, convolve this s of kx comma ky with f of kx comma ky. So that would anyway multiplication factor of x naught y naught would come out. Then there is this, you take this inside the summation, shifting property again, and this is going to give a delayed versions. So this anyway, let me first keep the summations here, m varying from minus infinity to plus infinity, n varying from minus infinity to plus infinity. Now it's going to have delayed copies of it, kx minus this value delayed by this when you are convolving it with that using shifting property. Similarly, ky for f would be delayed by integer multiples of y naught. Okay, that's all. So this is the final expression for the two-dimensional Fourier transform of a signal that you have obtained as a result of multiplying your 2D function with a 2D impulse train. Now let's try to draw that to get a bit more clarity about it. Okay, assume that this is your f of kx comma ky, right, for varying values of kx and ky magnitude spectrum. Let's try to now plot the magnitude spectrum for fs of kx comma ky. How do you get that? When m and n are equal to 0, you have its copy placed at the same copy as the earlier one. Then for example, you have m equal to 1, right? Then you have copies which are delayed in the x direction. Okay, then you take different copies of it placed here. This, yeah, the shape is becoming difficult to handle, so let me just draw a simple diamond kind of shape here. Makes my life easier. Okay, suppose that's my Fourier domain. Okay, now I'm going to have copies of it now placed. For if you look at carefully the way the x and y are changing, you will have different copies of it placed. N equal to 1, let's say, that's equivalent to having copies on y naught. Bear with my wonderful drawing skills. Okay, this is your ky, and now this is, let's say, you have here x limit, and here let's call it as yl. This is minus xl, let's call it, and this is as minus yl. This copy here got placed at 1 by x naught, and here this copy is placed at 1 by y naught, and then there is a periodic nature of that. Okay, so again, now you could look at the 2D sampling theorem here in similar lines to what we have seen in case of 1D. So what can we say here? F of x comma y can be recovered from f subscript s of kx comma ky if what should be the case now? There should not be any overlap caused due to placements in the x direction. So again, you could see this length is xl, this length is xl. So 1 by x naught should be greater than or equal to 2 times xl, and also here the placement is at 1 by y naught, next copy, both positive and negative, so that should be greater than or equal to 2 times yl, right? The both conditions have to be satisfied. Then you could recover f of xy from the Fourier spectrum of fs of kx comma ky. Otherwise, as usual, there is aliasing, right? I hope that is clear to you. In the next video lecture, we'll continue our discussion. Thanks for watching. See you. Bye. Take care.